So for who has not connected last week, but I guess all of us will connect also last week. So my name is Filippo, I work for Arm Research. Danny is a colleague of mine, he works for Arm Research as well. We organized this series of webinars, this is the second one, in order to, let's say, disseminate and educate some of the MaX member to some of the tools we're using to do co-design for next generation HPC system, with a particular focus on how to simulate and emulate new feature for high-performance computing code. We covered already what SVE is about last Tuesday, so there's not going to be an introduction again on SVE today. And we talk about Gen 5 and simulation Tuesday with Javier, and I don't think Dan is going to touch the topic again. Today, the topic is about ArmIE, that is an emulator, so works slightly different. And Danny will present what ArmIE is, what ArmIE does, what we can do with ArmIE, but also we'll go through, I suspect we're going through an example. There is HPCG as a use case, just to give you an idea how we apply this tool to a real, in this case, a benchmark, but it can be applied to a real code. So I will be on mute and possibly also fade away on the call later. We are recording this talk as well, and the slide will be made available. There's no NDA information in it. Just patient next week, and then we will do everything. So Danny, I leave the call to you. If there is any question, I don't know what's Danny's preference during the talk or at the end. It's really up to him.
Yeah, it's okay both. I mean, if there is a question in between the slides, yeah, I can answer. It's
okay.
The same for me. Okay. Well,
okay. So Danny, it's up to you. Go ahead. Thank you.
Thank you. Well, so as I'm Danny, as Filippo already said, and as he already said, I'll be presenting and talking about the ARM Instruction Emulator, ARMIE from now on, just to make it shorter, and how you can use this emulator to evaluate SVE applications, or even to develop from scratch an SVE versions of applications you may have already. So regarding the presentation, we will start by introducing the application, the benchmark we use that we are going to be using later, HPCG. We will talk about some of the optimizations we made to the original code, so we can so we know with a bit of details what are we seeing with the emulator. Then I will present the emulator itself, ARMIE, which is actually based on Dynamo Rio, and then I will talk about the scripts we use for post-processing the information given by ARMIE. And by the end of the presentation, or mainly the main body of the presentation, will be about how to analyze an application with the emulator, like which are the metrics of interest that you can get from the emulator, and how you can use them, and what are the meaning of those. So let's gonna start with HPCG. HPCG, it's a benchmark. It's a benchmark that it's used for ranking top 500 HPC systems. The main reason we choose this application for different studies, like the one I will be showing soon in the presentation, is mainly because the kernels that you can find in the benchmark are actually representative of real world scientific applications that we usually run on HPC. In this sense, for example, kernels from HPCG, you can find them in computational fluid dynamics, like OpenFOAM, or in computational photography. You can also find it in the ML library. I'm not talking about machine learning. It's a multi-grid solver library developed by Sandia National Labs, if I remember correctly. And also, another interesting thing about this application is that it's not only about the floating point operations you can do per second. It's also about the memory bandwidth. And in fact, the benchmark itself, it's memory bandwidth. And also, since the kernels are representative of real world workloads, it also helps us to develop and to motivate improvements in some libraries that we also offer as ARM. Regarding what HPCG does, so in one line it solves the linear system, a linear system. How to do how it does this? It uses a conjugate gradient method. So basically, it implements an iterative solver. The conjugate gradient is it's preconditioned. For the preconditioning, it uses a multi-grid method and with a Gauss-Seidel on it. The rest is it's a conjugate gradient. We don't need to know what it does. It's just information about the application. The main takeaway from here is that all of these, all the data structures represented in HPCG are mainly in a sparse matrix. And the main kernels or the ones that takes more execution time are the sparse matrix vector multiplication and the Gauss-Seidel, which is 70% of the execution time. And the problem with the Gauss-Seidel is that it's not parallelizable, but we can do a bit better. We can actually parallelize it. To parallelize this benchmark, you can use different techniques, parallelization techniques. We choose two of them. This is the first one, is the multi-level task dependency graph. This parallelization technique consists in trying to process each node, right? If this is our grid, which will be represented in a sparse matrix, node 0 will depend on 4, 5, and 1, and then the main idea here is to process the nodes as soon as all its dependencies are fulfilled, and are fulfilled in the sense or how they would be fulfilled in a sequential execution, right? In sequential execution, we will process 0, 1, and till 15. So looking at how, at an example, first we will process the node 0. This we'll call the level 0. Then afterwards we can process the node 1, which only has node 0 as dependency, as immediate dependency that should be processed before the processing the node 1. Then at this point we can process in parallel the node 2 and 4 because both of them have all the dependencies needed already fulfilled. And then we can continue with the same algorithm just to till we process the whole grid. So basically here the parallelism is get in each of the levels that you may process more than one node at the same time. And the parallelism is not perfect. It's not stable. You can have more parallelism, and you will have more parallelism in the, let's say, at the mid levels compared to the first or the latest levels, where you will have really low parallelism. So another technique you may apply to parallelize the HPCG benchmark is the block multicoloring. Here is that starting from the same grid, we apply blocking. Basically, we group different consecutive nodes together. After you apply this blocking, then you can color the blocks in a way that blocks with same color don't have a direct dependency between them. So for example, if we take the red blocks here, nodes 0 and 1 don't depend on nodes 8 and 9. And the same applies for the green, yellow, and blue blocks. They don't depend on each other. Now what you can do here is that you can process in parallel all the blocks with the same color, right? So for example, we would be able to process in parallel red blocks, but within each block, you must process sequentially the different nodes, right? Here, this block and this other block can be processed independently, but nodes 0 and 1 must be processed sequentially. Same for 8 and 9. The amount of parallelism you can get with this technique is higher and more stable than with the tasking approach. Then how do you apply this in HPCG? In HPCG, we actually, since it's implementing a multi-grid method, you have different levels of the same grid, which are of different sizes. For the finest levels, which is the biggest level of the grid, we use the parallelization techniques that provides less parallelism, but it's still okay with the size of this grid. As for the coarser levels, which offer a less number of nodes, we use the technique that offers more parallelism. Yeah, this link, I need to change it. I was changed before. Then, well, going back, basically we apply both techniques at the different levels of the grid used in the benchmark. Then how this performs? So basically, here is that we put everything together. We are able to parallelize with OpenMP the main kernels, and that ends up improving the application scalability, as we can see, with the in the plot, right? Dark blue is the baseline, which is the reference code, and then the light blue is the optimized neon code that we where all these optimizations that I just explained are implemented. And scalability, it's I mean, it's better, plainly better. In fact, the gap in performance we can see at 7 nodes, it's expected to increase at higher core count. And well, as a side note, these results were presented at SC18, and the feedback was we got a positive feedback. Then why I was explaining why do you care about HPCG? Maybe you actually don't care about this application in general, but you may have a similar application where you had your application, you optimize your application, and then it's like, yeah, it scales better, but single thread performance, it's hard. So you may want to use or you may want to benefit from some other programming models, or in this case from vectorization. But for this, in our case, in SVE, you may depend on simulators, or as we did, we use the different tools. In this case, an emulator, which is ArmIE. Then, regarding ArmIE, this is the main picture of how it works. So you have an RBA, your binary, which also includes SVE instructions, and then you will use DynamoRio, and DynamoRio will have a client, which is the emulation client, which will be in charge of emulating the SVE instructions, or the non-implemented instructions in your hardware. The native instructions, the instructions that you have available in your hardware, they will go through DynamoRio and they will be executed natively. Then the Arm Instruction Emulator, ARMIE, the emulation client, has an emulation API that can be used to build clients, different clients on top of that. Right now we have 3 clients available. One is the memtrace client. This client, it generates a memory trace of your application. Then the inscount client is one that it basically counts instructions. It counts the total dynamically executed instructions, and also counts the total dynamically executed SVE instructions. And then you also have the opcodes client. This client basically counts opcodes. So basically, it has a counter for each instruction executed, and it will report the counter. But then you could think that, well, I may want to prefer to use a simulator with my application. I trust more my simulator. Well, you may have some other reasons to use ARMIE. For example, one of the reasons to use ARMIE is that it's a fast functional emulator. So basically, emulation time compared to simulation time will be much lower. And actually, in fact, the emulation time the time to execute your application through ARMIE mainly depends on the number of SVE instructions your binary has. Since the instructions that are not SVE and that are implemented in hardware, not in your hardware, they will be executed natively. So there, the overhead would be really, really small. Also, it's easy to develop new instrumentation to use with ArmIE. And so you can easily create your own client that talks with the emulation client to gather the metrics you are interested in. And also you can, and you can, on top of that, you can develop your own post-processing tools to process the information you gather. It's freely available, which in case of some simulators, if you wanna, yeah, you can get it for free. It's open source, but if you want a good performance model, it's usually a bit more. It's harder to get it. They are not as available as the source code of the simulator itself. And it's partly open source. The API to build your instrumentation, it's an open source project, so you can check it, you can contribute, so on. But yeah, there are not only good things about the emulating, about ArmIE. There are some drawbacks. Is that ArmIE is not cycle accurate. So by running through ArmIE, you lose any timing information you may want. And the reason for that is that you are not simulating anything. You are just replicating the functionality of the instructions you don't implement in hardware. It's not also, so, and in the same line, it's not a simulator. So you require actual ARM hardware to run your ARM binary with SVE instructions. The only thing ARMIE will do will be to emulate the SVE instructions, but not the ones that can be found in hardware. And you cannot do architecture modeling. So basically, this is mainly emulating. With ArmIE, it goes around the application, not about the hardware.
Carlo from Cineca, just to understand maybe the same question I've done yesterday. Anyway, this is able to run executable compiled with SVE, right?
Yes.
Okay.
Yes, I mean also with even if it doesn't have SVE, but any ARM ARMv8 compatible binary will be able to run through ARMIE, and ARMIE is meant to run these binaries with, in this case, with SVE. It's a usual use case.
Yeah, because I think one of the first goals could be to understand if the SVE will be used or if they are not used at all from the
Of course.
compiled code.
Of course, and we are gonna look at that. Because you can get that information from the emulator, actually. So, well, moving on. How to use this emulator. And then we will move and on how you use it, how you get the information you can get. So basically, you compile your application with an SVE capable compiler. So you have a binary with SVE instructions, and then you run it through ARMIE. To run it through ARMIE is this line. It's the ARMIE. Then you specify the vector length you want to emulate. So you can choose from 128 to 2048 in steps of 128 bits. You can specify your client, or you cannot specify any client, and then you will just run the application. This is useful to check for correctness only, and then your binary. You can also use region of interest markers in the code you want to run through ARMIE. So if you are going to get a memory trace, you are only interested in one part of the code, so you can delimit this part of the code and then only get the information from there. As right now, this region of interest is not implemented on all the clients, though. And right now, there are 3 SVE-ready instrumentation clients available that come with the ARMIE, with the latest ARMIE version. The ones I already mentioned: the InsCount, the opcodes, and the memory and the memtrace. More in-depth information about how ARMIE works, it's available in a public blog that we really we posted some months ago already, but it's still you can still use it. The information there, it's still updated. Then, regarding what the information you can get with the application, with ARMIE. First of all, you're gonna see now two different two different versions of the application in all the plots, all the information. These are the baseline and the optimized, as we call them. Is HPCG is the same. The baseline is the reference code you can download from the web page. The optimized is the one where we actually implemented all the optimizations, the prioritization techniques I explained before. On top of these prioritization techniques, there are also some minor performance improvements by using loop function, unrolling, improvements in the memory allocations, and some data organization. And all the results that we are going to see here are from binaries obtained with the ARM HPC compiler. Then we start with the instruction client, which is usually like the most simple thing you can get. Is just number of instructions. No, total instructions, SVE instructions is what you get. Now this metric can be used in whatever way you can think of. It's mainly used to know the percentage of SVE instructions you have in your code, and also you can compute the reduction in terms of instructions when changing your vector length. Remember, you can specify the vector length you want to emulate of your SVE unit for each execution. So you may want to see percentages of SVE instructions for different vector lengths, and you can see also reduction in terms of instruction. So, for example, what I was saying is plot like this. On the y-axis, we show the dynamic total instructions. On the x-axis, we have categories for different vector length in bits, and then we show at the bottom of each column is the percentage of SVE instructions, and then on the top, the percentage of non-SVE instructions. So we can see that for HPCG, the percentage of SVE instructions, it varies. And everything is relative to the case, the baseline case, the first column. So everything is relative to that number. So the first thing we can see is that optimizations actually increase the number of instructions. That is expected. But first thing to see, right? Percentage of SVE instructions are a big chunk of the total of the total number of instructions. And if we take a look at how it increases in this, when we have a huge or the biggest vector unit we can, or the widest vector unit we may have, the percentage in comparison to the total number of instruction decreases, which is not something that you may want. So this information can be used. You are trying to decide which is going to be the best vector length for your SVE unit. So you can just grab the applications you want to run, or that you will run in your platform, and then see which is the one with that has the highest percentage of SVE instructions compared to the total number of instructions. And yeah, you can see that for both cases, more or less behave the same. Wider vector lengths do not seem to benefit the application. But at the same time, it's like, yeah, I got a 60%, but is that expected? Well, you can check with compilers how much vectorization was actually done. If you see that a lot of your loops, all of your loops were vectorized, but still you have a low percentage of SVE instructions, then maybe the problem is that you are not being able to vectorize as much as you think in the beginning. For example, and here is something that you may do, right? You get, for both versions, you may get how many loops were vectorized. Here we compare an SVE capable compiler, GCC, and the ARM HPC compiler, and we also put for reference an AVX2 compiler. from Intel, not the Intel compiler. Intel compiler does not generate SVE. I don't know why sometimes people ask me that. No, Intel compiler doesn't generate SVE. All AVX 512, but not SVE. Then, for example, if we go to GCC and the ARM HPC compiler, we can see that for the baseline, it's okay. Everything was vectorized. So the percentage of vectorization we were getting was expected, considering that we already know about our application and what to expect. But in the case of the optimized version of the code, we see that, hey, we're not vectorizing everything. And at the same time, but we were still seeing a considerably high percentage of SVE instructions. But with this, with the percentage of instructions, with the client and with information from the compiler in this case, we can see that we could increase more this percentage of SVE instructions. And for example, in this case, where that some reverse loops with outer loop unrolling weren't vectorized. So we may want to reorganize these kind of loops, or rewrite them in a way that they are more similar to this one, and therefore are vectorized. But counting instructions is not the only thing you can do, and actually probably is even though you can get useful insight, is not the only insight you will be able to get. So moving on to the memory trace, the client, the mem trace. So this is based on a Dynamo Rio client, and the non-SVE tracing is done by Dynamo Rio, and then the SVE tracing is done by ArmIE, or by a client that works on top of ArmIE. Here you can, with this client, you can specify your region of interest. You just need to execute a specific instruction in your code. It's usually easier to just define a function and then you call it. And then two trace files are generated, one for the non-SVE and then another one for the SVE memory accesses. In both files, you will have a shared synchronized counter that it can be used to order both traces and to know what is happening before what. And one thing you actually want to do before post-processing these traces are to merging them, so you end up with only one trace, not with information you want. Regarding the mem trace format is sequence numbers, the thread ID, the SVE bundle. This is to identify if you are on a gather scatter SVE instruction, or if you are in doing a contiguous load, etc. Then you have the information if it's a write or not, the data size of your memory access, the data address. This is for vector instructions. This is the starting memory address you access, and then the PC. And then how to use this client is more or less the same. ArmIE, then you use the emulation client, that this is for tracing in the Dynamo Rio part, and then for tracing on the SVE part, and your SVE binary, and you will get two files, as I already mentioned. Regarding the merging, it's, again, since you have a counter, like the first number, you just need to grab two files, order them. The region of interest markers are specified with this -1 for the start, -2 for the stop in the second field of the line. And then to differentiate between non-SVE and SVE traces, we use a different separator in for the first field. And then things you can do with the traces. So you can parse the traces, for example. Is the easiest thing to do, and then you can parse them and print them in a way that it's easier to understand, with higher verbosity and better readability, and extracting metrics as well. So for example, here you have the bundle information. So this is for a gather or scatter. I cannot see what it was now. Okay. Bundle started. Yeah, I cannot see what it was now. I don't remember. So basically, this is a gather, scatter. So a load. This is a load. This is a gather, and all the information of this gather, memory position accesses, how many lanes were enabled in these memory accesses. This is non-gather accesses. Basically, this is printing everything in a way that it's human readable, even though you need to learn first to read it, of course. But now going back to a more probably understandable, right? Plots and tables. This is everyone could understand. So basically, with the memory traces, you can trade you can get the average vector utilization, which is how many lanes of your SVE vectors were enabled when, in average, when accessing when accessing memory with SVE instructions. So in this case, again, for the two versions of the code, we have around 82% of the lanes of your vector were enabled when accessing memory. If we don't look at the average and basically we split this information, we look a bit further. In the y-axis now we have the percentage of access, well, the ratio of accesses. This is not a percentage anymore. And in the x-axis we have different bins for the memory accesses that we're using from 0 to 33% of the vector, from 34 to 90%, 99% of your vector, or 100% of the vector. So basically here, all the predicate, not the full predicate was true. And we can you can see that in this case, around 75% of the memory accesses were instructions where the predicate was almost true. This is again a method that you can use to see how well are you or how well are you actually using your vectors, right? Because if instead of having this 75% here, it would be in this other bin, it means that most of the time you are not fully utilizing your vectors, and this will impact performance. And apart from looking at vector lane utilization, you can also look at the memory instructions breakdown. So in this case, we are splitting between SVE memory instructions and non-SVE memory instructions. Again, y-axis is percentage of accesses. And for the SVE instructions, we are splitting them in contiguous loads and stores and gather and scatters instructions. And for each of them, with the full predicate, the all lanes enabled, and with the predicate where some of the lanes were set to false. So basically here is like the most number of SVE memory accesses were contiguous memory accesses with all the lanes enabled. This is a good thing. But at the same time, the vast majority, or not the vast majority, yeah, it's around 60%. So basically, 60% of our memory accesses are with SVE instructions. Again, this is something that it's what you expect if you are vectorized, or you expect a high vectorization, a high vectorization of your code. You expect this number, not these memory accesses, to be higher. And then inside, a summary of the memory traces. So first thing to check is that if you're having a poor vector utilization. And the reason you're having a poor vector utilization could be because the loops are short compared to your vector width. So a short loop is not the same compared to a 128 vector unit or a 2048 vector unit. The amount of the number of elements you can fit in each vectors are different. So that could be a reason of the poor vector utilization. Then you need to check back at your code. Can I change that? Is it worth it? Then it can also be because you have conditional statements that can disable some lanes of in your predicate, some registers of your predicate vector, and therefore the vector utilization will not be as high as you may be expecting. Then another thing you may realize is that mostly all of the memory accesses are gather scatter. In general, contiguous loads and stores are usually preferred compared to gather scatters, just because it's usually easier to load contiguous memory contiguous memory locations that the memory locations that you don't even know where they are, right? So in this sense, if you have in your code, if you realize that after analyzing the memory trace that you have too much memory gather and scatter, you may want to ask yourself, can I reorganize the data? I mean, this is something that we actually did, right, in the past. As I mentioned before, optimizations weren't only parallelization, but also memory allocations, data reorganization, and the reason for that was this part. We realized that we needed too many gather and scatters, so we needed to reorganize the data to improve that metric. Then you may have a low percentage of SVE memory accesses. This is if your number of SVE instructions was already low, then maybe it's only that. If not, you may want to check in deep your code to see what's happening here. And also, I'm not doing it here, but it's usually useful to compare what's happening against Neon to see if you're actually improving the vectorization or not. And this also applies for the instruction count. And some of the things that you can do with your memory trace. So we built a really, really simple cache simulator in-house to study these memory traces. Again, it's a really simple one. It supports only single core and several levels of cache, but we don't support multi-threading. And we also added support for prefetcher plugins to the cache simulator. Right now, only simplest straight prefetcher is what we have. This is an in-house simulator that basically you can write it in during the afternoon. It's not such a complex simulator. And then, you can add some parameters like cache size, so on. And then from the memory trace, you can run it through the cache simulator. You may write that. You can write it as complex as you want or can write. Usually requires time. The more complex, the more time you need. And then you can see things like the percentage of hits. In this case for L1, L2, or L3. Then in this case, we're showing for the two versions of the code. But this is something that you may get from the memory traces. At the end, is there's a trace with memory accesses. So what you do with it, you have the information. What you do with it is just depends on what you want to do, or what are you looking for in the trace. And then here at the right, we can see the average number of cycles per memory access with that the cache simulator computes. Again, this is something that it's really simple. In general, you can correlate what you can see in this simulator with real hardware, but it's in that sense it's pessimistic, right? So in the sense that if you're getting an 80% hit ratio in real hardware, here getting a 60%, it's feasible. And the more advanced the cache system of your hardware is, the more difference you will see between this simulator and your real hardware. Then closing, all the things you can do. The methodology you can use when using this emulator. So basically, I've shown here that the compiler analysis. This is not something that you do with ArmIE, but with the compiler itself. Then the cache simulator statistics. This is that. Then you also have the dynamic instruction count for non-SVE and SVE instructions. And the vector utilization and the memory memory accesses breakdown, and you can use this, and we actually use it. That we have our application. We check all these. We get all this information, and then we produce an optimized version of the code. Right? I want to emphasize that all of these metrics by their own are not as meaningful as the addition of all of them. In the sense that a lower percentage of memory accesses, of SVE memory accesses, doesn't mean anything if you or it's hard to get some useful information from them from that if you don't have also the percentage of SVE utilization. At the same time, the percentage of SVE utilization by its own, it's not, let's say, it's not enough metric, but you might also want how much of your code was actually vectorized. And for the CAD simulator, it's more or less the same. Yeah, I'm getting this number, but what about the SVE utilization and my memory accesses? So it's everything. It's a whole thing that we used together to optimize the application. And again, this is like any other software development. You have your application, you pass it through the methodology you create, you have an optimized version. Then you pass it again until you are happy with the performance you may get. And then here a summary of the metrics you can have. The dynamic instruction count, the percentage of SVE utilization, the percentage of SVE contiguous memory accesses or gather scatter, the hit ratios in the L1 cache or L2, L3, whatever you model in your cache simulator, and variations in the average of number of cycles per memory access. And now to just show what's next in ARMIE, because it's gonna be more. So next version to be released in the next few days, it's ARMIE 19.0, which is mostly bug fixes. So that's not a good bug fixing. It's new, but not in terms of new features. But for the 19.0, there will be another release of improved clients, a new instruction trace client, and also improvements in the region of interest and on the client options, in the sense that, for example, only tracing your binary, the instructions executed in your binary, and not shared libraries, etc. And also for future versions, it's a better multi-thread support, emulation API updates, and debug functionality, which is something that it's still missing, debugging with ARMIE. And then as a final, final remarks. So basically, what I show here is that you can use ARMIE to evaluate SVE applications, and since emulation time is shorter, it's faster, you can actually use more realistic input sizes. In fact, all the numbers I presented here from HPCG were obtained from executions through ARMIE using an input size that you could use in a real scenario where you wanted to submit your HPCG performance for the top 500 ranking. Then again, the non-SVE instructions have near zero overhead. You just execute them in your hardware. You don't need to emulate anything in there. And again, SVE application test and validation is possible without having to go through a simulator. If you don't care about any metrics, you just want to see if your SVE application works and that everything is correct, you can just run your application through ARMIE. See that it finishes. Performance is not, you won't be able to see performance, but you will be able to see if the SVE implementation with intrinsics that you used, it's actually working or not. Then, since it's an emulator, right, the evaluation depends on time agnostic metrics, because as an emulator, we don't have any timing information. So you rely on instruction counts, memory traces, in a future instruction traces, or in depth code. And again, you need to look at all the metrics. By their own, the value, they have little value. I mean, it's just something to consider with ARMIE. But on the other side, you may want to create your custom clients to see the metric you are missing, and you have the possibility to do that using the emulation API. And post-processing, with post-processing, you can extract finer grain metrics. And again, this is something that I want to emphasize as well. ArmIE does not replace simulators. All tools have its purpose. No, you cannot use for the same ArmIE an emulator and a simulator. They have different targets. And yeah, with this, we can finish. Thank you, everyone. If anyone has some questions, just let me know.
And Carlo, I'm wondering if I'm not wrong, the Intel Inspector tool provide, together with the memory access and vectorization and other stuff, provide also a rough estimate of the roofline model or the position of your execution in a roofline model of the architecture. I'm wondering if there is, from the data you have in output, one can draw a sort of roofline graph out of the execution.
Yeah. So this is something that right now it's a bit tricky, because for a roofline, I mean, depending the metric you want to use for the roofline, but let's gonna assume that you're gonna use flops in your.
In general, we can think of relative term, so memory bandwidth versus number of vector instruction or peak vector instruction.
Yeah.
So I don't know if in the emulator you can put these kind of parameters.
No, you cannot model hardware in the emulator. The only thing, so you can get memory. No, for example, you could get a memory trace and then post-process the memory trace. You basically script or application that as an input has the memory trace, and then use this memory trace to compute the metrics you want. But no, you cannot model no real hardware in the emulator. You can the emulator only emulates the behavior of the instruction of an SVE instruction, but not latency, not no, latency in terms of instructions, hits or misses in cache, if it's a memory access. It doesn't emulate that. It only emulates the behavior of the instruction. So if I'm loading this vector, it emulates not loading the vector, but it doesn't simulate how many cycles I will spend, so on. So this is something that you can do afterwards with post-processing, but at the same time, each tool has its, as I said, each tool is for the different thing. If you want to model performance, then probably it's better to use a simulator rather than an emulator. In general, the emulator moves more around the software than the hardware in this case.
Okay, thanks.
Yeah, welcome.
Just another question. You said that with ARMIE you can run realistic kind of application and data sets.
Yes.
You have, well, again, from what I know from, let's say, the tracing tool of other tracing tool, not only Intel, they are quite, let's say, quite verbose and produce huge amount of files, and they tend to allocate a lot of memory, so that at the end, when you have to run a realistic, let's say, input, they finally end up crashing, or let's say crashing the system, or
Yes,
providing too much data.
yes. No, I agree. I've actually faced that problem before. So it with ARM, it depends on the on the information you want to get. For example, if you just want the number of instructions, the INSCON client, the amount of memory you're going to use is the same as it will use the application natively. If you want to get a memory trace, then it's a bit more tricky. It's not a problem of memory usage here, but more about disk usage, because the trace it is a text file, right, with different lines specifying the different information. It's actually a CSV file. So here you are more limited by the size of the trace rather than the memory. Memory usage would be the same. Actually, the impact in memory usage when in our experiments, when emulating big applications, it wasn't noticeable. So basically, the memory usage was the same as in a real execution without SVE. But in the other hand, not generating a huge memory trace, for example, makes the post-processing or the processing of this memory trace harder, right? Because you need to read the file. So the bigger the file, the the more time you will get processing the trace. But again, the execution will still be faster than the simulator if you are able to extract the information you want from your trace fast enough. You are still being faster. But it here depends on the information you need and the information you want to extract, and also not how much region of the code you are interested in. A memory trace of 3 instructions is gonna, that not just makes sense, right? 3 instructions is gonna be lower than 30, and the same applies for higher counts. But in terms of crashing, in any of our experiments, we were able to make it crash due to memory requirements from the emulator.
Okay, thanks.
Welcome.
Okay, I think, Danny, I think Filippo has disconnected
Yes.
minutes ago. So I think if there are no more questions, I think we can close the session here. I don't know if anybody else has a question. Seems not.
Okay. So I'm closing this. Well.
Okay. So.
Thank you. Bye bye.
Everybody, bye bye. Thank you for attending this webinar, and see you maybe in the next time when we will have maybe some data or something to share about our experience with the tools. Bye bye.
Bye. Thank you.